Okay, so we're back with week 8, where we're going to continue discussing the imp language. So we're sort of about halfway through the imp chapter. And the plan for the rest of this is to extend imp from the basic expressions that we saw last week to add two main features that imperative languages have, which are variables and commands, which is what a lot of PL people call statements. So we need to be able to model things like the current value of a variable or evaluation that might not terminate if we have loops, for example. And we'll see how to do all of that in the rest of this chapter. Okay, so to start with, we'll just quickly extend expressions to include variables in them, because at the moment all the expressions that we've got are constant expressions basically. So they have a value, but they can't depend on any external data. So this is where we need the map stuff that we did last week as well. So we need to be able to keep track of the value of variables or the values of variables for particular evaluations. So we won't be able to say things like what's the value of an expression. We'll be able to say, given a state, what's the value of an expression in that state, right? Which is similar to saying, if I evaluate an expression in a normal programming language, it depends on what the state of memory is like to tell us what the value of that expression is going to be in general, if it's not a constant expression. So that's what we're going to use the maps for. So if you remember, we defined total maps and partial maps in the maps chapter. So we're going to use a total map here. So the semantics that we're aiming for is that in any state, every variable has a value. And we're going to use natural numbers as the values. So we're not going to be able to have, for example, Boolean variables or variables with other types, right? We're just going to keep it simple to only have natural number variables. And we're going to have a default value. So when we talk about the empty state that all other states are built on, we'll make it out of a total map that has zeros at every position. So this is a simplification, obviously, on real programming languages, because in some languages this makes sense, but in other languages the default value of a variable wouldn't be zero necessarily. It might be some other well-defined value, or it might be some value that's just happens to be sitting in the memory and so on. So we're going to be more precise than that. We're going to assume that every variable, if it's otherwise unassigned, starts out with the value 0. The initialization is 0. So that's what these are. This is a type, so state is a type of maps, and empty state is the particular state that sort of starts with every variable having its default value. Okay, so looking to expressions again, then we can extend the definition of an arithmetic expression to include a case for variables in expressions. So in this case, we're going to call it AID. It's going to take an ID, which is the identifier of the particular variable that's being referenced here, and that's all you need in that constructor. Okay, all the other constructors are the same, but we now have a new base case where the leaf, if you like, of an expression can now be a reference to an identifier. And strictly speaking, all of our identifiers are just identified by numbers, but it's a bit tedious to have to use the numbers all over the place, so they define a few aliases here for X, Y, and Z to make it a bit easier to read the examples. And then Boolean expressions don't involve identifiers directly because we're not allowing Boolean variables, but they obviously, everywhere they use an arithmetic expression, they're now talking about the new kind of arithmetic expression, the the ones that can have variables in it. So this implies that you can have variables inside Boolean expressions as well now. Okay, so that's the syntactic extension. We've just added one constructor to represent the case where we have a variable. So there's nothing yet about states and things, because the states are only needed when you try and do the evaluation. Now, remember from last time, we had an evaluation function sort of approach to start with. So we had this function aeval, which in the first version took an expression and returned a natural number, arithmetic expression. Now we have to add another parameter here, which says, well, it's not possible in general to evaluate expressions just by themselves. You need to know what the state is that you're going to be using in case you come across some identifier in the expression. So this st parameter is that state, and you'll see that all the cases are very similar to before, except the new one is here. So this one says that if you come across the variable x, remember x is just an ID, then to work out the value of that expression, you just apply the state function. Remember, the state function is total. It must have a value for every variable. So you use st as a function, and it will give you back a natural number, which is the value of the variable x in that current state. Okay, so that's pretty simple. The recursive calls all have two parameters now instead of one. So the st is passed unchanged down to the children if there are sub-expressions, and that makes sense because the evaluation of an expression doesn't change the state, doesn't change memory at all. It just uses the current value of memory at every different position in the expression. Okay, so that's aval. Bval is basically the same as before, except it adds the state parameter, right? So we don't need a state parameter to think about the value of a Boolean expression itself, but we do if we have an embedded arithmetic expression. Like in this case, we need to evaluate A1 and A2, and to evaluate them, we're going to need some state to use to do the evaluation. So that state is passed into aeval and also into the recursive calls of beval for the same reason as we need it for aeval. Okay, so given those two things, so again, this is computational definition. Remember last time we talked about computational versus relational. So this is definitely computational because we can always just crank the function aeval or beval with a state and an expression, and we'll get a number or a Boolean value back. That's well defined. You can't go wrong, mostly because we're deciding that the default value of variable is given by whatever the state says. We don't care what it is as long as it's going to tell us something, and it must because it's a function. Okay, so we can use this to do some evaluations. So for example, here we have the expression 3 plus x times 2. And obviously to do the x times 2, we need to know what x is. So there's a state here, which is the empty state, where x has been updated to be 5 instead of 0. So we'd expect this to be 5 times 2 plus 3, so we should get 13. And again, because this is just computational definition of the semantics, we can just run this function by simplification, and we get the answer we expect. Similarly, in this one, we're saying, well, this is true and not x is less than or equal to 4. Right, so again, we need a state to tell us what the value of x is, and again, we're using the fact that x is 5 and everything else is 0. So we expect this to say less than or equal, so if x is less than or equal to 4, well, it's not because of 5. Right, 5 is not less than or equal to 4, but notting that gives us a true, so this expression in here gives us true, and then we've got true and true gives us true when we evaluate it. So these are just simple examples, just showing how the state functions are used to work out the value of particular variables. Of course, this is not really the full power of imperative languages because the state can never change here. So whatever state you start with is the same state you end with after you've evaluated an expression. So what we need are statements, or we'll call them commands here, which let us use things like assignment statements to actually update the state. And then we need to take into account that there will be different states at different parts of the evaluation. So I'll stop here now and we'll pick up in the next piece with commands.